Okay, I'm going to talk to you today about vectors, what they are, and how we can do some work with them. So we learned from our cartoon that a vector is a mathematical quantity represented by an arrow, okay, with both direction and magnitude. So the length of our arrow here, how long this thing is going to be our magnitude. Now, if we're talking about like a distance, or excuse me, if we're talking about a displacement, it makes sense. It's going to be the length is the distance, or the displacement. But if we're talking about like a velocity or an acceleration, the length of the arrow will still represent the magnitude. So an object with a velocity that looks like this is generally slow, whereas something with a velocity that looks like this would be fast. Okay, this end of the arrow, this right here, is called the, that's terrible. Anyway, this end right here is called the tail, and this end over here is called the head of the arrow. Okay, so we have a couple of things, operations then, that we need to do with vectors. First, if we wanted to take a vector times a scalar, so like if I wanted to take 3 meters per second times 2 seconds, okay, all you're going to do is multiply the quantities, the magnitudes, okay, and keep the direction. West. Okay. So I should have gone with east. West is to the left. It looks like this, really. If this is 3 meters per second, and then another 3 meters per second, and then another 3 meters per second, the total is going to be, 2. I only multiplied by 2, sorry. Okay. The total here is going to be 6 meters per second, and it's still going to be west. It's still going in the same direction. Okay, it is possible to multiply a vector times a vector, but we're not going to do it. There's a couple of different ways that it can be done, and there's just some fanciness to it. That's an issue for college physics, not us. Okay, in the meantime, we need to learn how to add two vectors together. Okay. Which is simple enough when we're looking at like this, it makes sense, but what if I have two vectors that are going into completely different directions? Okay, so the rule when we add vectors together is we need to draw the vectors, and I mean that, and you know I mean that. So we're going to draw the vectors, and we call it head to tail. So if I need to take 3 meters per second west plus 2 meters per second south, I would draw the first vector here, 3 meters per second, and then I would draw the second one south, 2 meters per second. Okay, this is how we draw them to start with, and then we're going to draw what we call a resultance, which is a big fancy word for the sum of the two vectors. Okay, we're going to draw the resultant from the tail of the first to the head of the last. And remember that the resultant here is going to be a vector also, so it still needs to be an arrow, not just a line. So when we do this, similar to here, but I kind of made it messy, we had 3 meters per Problem is I need to write it above here. 3 meters per second here, 2 meters per second there. My resultant is going to go from here to here. But it's an arrow, right? So it's got to be like that. Okay. There are 2 ways we can add vectors together. I'm going to show you one of them right now, and then I will show you the other one in a few minutes. I need some stuff that I forgot over here, so give me a second. The way we're going to do this first is by, it's called graphically, and it's exactly what it sounds like. We're going to draw the picture out, there we go, to scale, and then measure our result. Okay, I'm going to turn the page. Oops, okay. Adding vectors graphically. Okay, so the first thing we want, and I'm going to give you a new set of vectors to add. We'll add, let's say, 39.6 meters per second east plus 52.1 meters per second north. Okay. First thing you need to do is sketch it so you know how it's going to go on your page. Sketch it like we did in the last page. So I would draw that east, and this one's going to be a little bit farther here north, right? And my resultant is going to go there. So I know when I go to draw this on my page that I probably want this first vector way down here at the bottom. Okay. So the first thing we're going to do is sketch, and then we're going to choose a scale. I can't get 39.6 meters per second at all, and I probably can't get 39.6 even centimeters across my page. So I need to decide how much I can get. Okay. I probably could get half of that, right? Well, maybe let's squish it over there. See, it doesn't even really fit. So we probably are going to need a third. So the scale I'm going to go with here is that 3 meters per second is going to equal 1 centimeter. Okay. And then we're going to draw our first vector. Remember, we decided that it's the bottom here. It needs to be at the bottom of the page. Okay, to scale. So my 3 meters per second equals 1 centimeter. It means that my first vector is going to be 13.2 centimeters long. So we're going to come down to the bottom of the page, and we are going to impossibly carefully draw that first vector. Okay. I think I've talked with you guys before about how when you measure a distance, we measure a length, we often start at the 1 and we go just a little bit, we go 1 centimeter past. That way we're absolutely sure we have what we're supposed to. So we're going to start at this 1 and we're going to draw this line out to, that's 13.2 centimeters. Okay. And then we're going to put an arrow on it, and we're going to do it very, very carefully so we don't make the line any longer. Okay. Then, to get this next vector here, this north, the temptation is to simply turn your ruler and draw this northern vector. But the problem is that we're not sure. You guys are surprisingly not as good as you think you are at making 90-degree angles, right? So is that here? Is it here? Oh, well, that's a 90-degree angle. Are you really, 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 really sure? Now I know I've got this line here conveniently on my page, but you don't always have that line. So you really need to measure the 90 degrees, okay, with a protractor. If you don't remember how to use a protractor, if it's been too long, there's usually a little plus sign here. You line that up at the very end of your arrow, right? Okay, make sure that the 0 degrees is lined up here, and then we're going to put a dot up at the top, okay, at that 90. And I didn't really hit that 90, did I? There. Okay. Now that I've got that, I'm going to measure the next one. Oh, this was easy. 52.1 is going to be 17.4, right? 3 goes on the left. 17.375, really. So we're going to do our best there. Okay. Line that up to here. I'll let you guys see it. Sorry. 17.3 3/4. Make sure it goes through the there. Okay. We're going to connect this down to there. Okay. And I'll draw my arrow here. Okay. Then I draw, measure it, 90 degrees. Okay. Draw your second vector. All right. And then we'll draw a resultant. Okay. So that's going to go from this corner down here. I know it doesn't quite fit on my screen. Up to that corner there. I've got this marker that kind of bleeds into my page, but pencils work best here because they don't bleed. All right. Also, if you make a mistake, it's okay. We're going to make that be an arrow. All right. Now we need to measure our resultant and the angle. Okay. So if I line up my one, the very end here, and then the very end of that resultant there. Okay. All right, remembering that I've got the one lined up there, I would call this 21.2 centimeters. Actually, let's remember our significant figures. And I would call it 21.20 even. Okay, and then to measure the angle, remember, get out the protractor. It's a little hard to do in this notebook here, but we'll just hope. Make sure this is lined up. Right, matches right there. This is lined up at the 0, so we would call this 51.5 degrees. Okay. Now, I still don't really have an answer, to be honest, because I have a length for this. So to get an answer, I need to take this and I need to multiply it by 3, right? Because each centimeter represents 3 meters per second. So that is going to be 63.60 meters per second. And then to talk about this angle. It's great that we have an angle, right? Because this isn't just simply northeast. Well, how much northeast? Is this northeast? Is that northeast, right? We need to decide where it is exactly. And 51.5 degrees northeast could mean 51.5 here, or maybe I drew them the other direction. Oops, not right now, okay. Maybe I drew the north first and then the east. Is it there 51 degrees or here 51 degrees? Now, first off, I didn't point this out. You'll notice that I measured the angle without any arrows on it, always, okay? So we need to tell which one that is, and the way we word that is we call it 51.5 degrees north of east. Because I've taken my resultant and I have swung this angle north of that eastern vector. Okay, so the of direction will always be the one that's a cardinal direction that you measured from. So if I measured from this, if I was measuring this eastern one and I never touched this northern one, that means I need to have the north of east. Whereas if I was going to measure this one right here, I would call it east of the north. Okay? So final answer here, 63.60 meters per second at 51.5 degrees north of east. Okay, and I know that it feels like a lot, and it is. a lot. We can do them mathematically as well, and we'll look at that tomorrow. But I wanted to make sure that you got this lesson in here today. This is how we do this graphically. You're going to like the mathematically better, and you're probably not going to use this again, but I wanted you to see it. It would be really, really useful, say, if you needed to add 2 arrows that don't meet at a 90-degree angle. There is a mathematical way to find this stuff, but it's ugly and you don't want to do it. And it actually is just easier to measure it out. Okay? Good luck.